Zan's Maths channel, and I'm now answering question number 5 from the October-November 2022 Pure Mathematics Paper 3, Variant 3 from the Cambridge 9709 specification. And here we have a question about complex numbers and Argand diagrams. So it says, on a sketch of an Argand diagram, shade the region whose points represent complex numbers Z, satisfying the inequalities that the modulus of Z plus 2 is less than or equal to 2, and that the imaginary part of Z is greater than or equal to 1. Okay, so Z is a complex number, okay, and we know that Z is equal to A plus B I. A complex number is made up of a part which is real and a part which is imaginary. And we can illustrate a complex number on what's called an Argand diagram. So we have an Argand diagram which is made up of like a horizontal and a vertical axis. Right? So the horizontal axis is for the real part of the imaginary number, and the vertical axis is for the imaginary part of the complex number. Okay, so one of the what's called the loci, one of the loci for Argand diagrams is the one where you have the modulus of Z minus the complex number Z1 is less than or equal to 2 or equal to 2. Let's say it's equal to a certain value. It's equal to a certain value. Okay, I'll put equal to first, and then we'll deal with this afterwards. All right? So basically, what it means is basically that, Z1 is a fixed point. Okay, and Z is basically going to be any position which satisfies this equation, you could say. Right, any point which satisfies this equation. And what it says is basically that the difference between Z and Z1, the difference between the points Z and Z1 has to be equal to 2. Okay, it has to be equal to 2. In this case, it's 2, equal to a certain value. All right, so for example, if I just draw a general thing, supposing our complex number Z1 was over here. Supposing that was Z1. Okay, then what we can say is that Z minus Z1, okay, would be this. This is Z. That's the complex number Z1. I'm not drawing this diagram, by the way. I'm just giving you a general idea of what this means, and then we can apply it to this afterwards. So that's the fixed point Z1, okay? And well, what we know is we want to find the locus of all the points which are a fixed distance away from this point, okay, where the magnitude of Z minus Z1 is equal to a certain fixed value. So if I draw a random point Z, okay, so supposing that's Z here, then this line between here and here is going to be, okay, if you think about it, this is going to be, if we think about the line going from here to here, it's going to be Z minus Z1. Okay, this line here. This is Z1 and this is Z. Okay, so if you think about how to get from, if I want to go from here to there, okay, so you can say this is like going, let's say, minus, if I want to go from here to here, I can say minus Z1 plus Z. Minus Z1 plus Z, you can think of it as Z minus Z1. You can think of this, the length of this line with the magnitude of Z minus Z1. Okay, so whichever way you're going, that length of that line will be this amount. And we want to find all the possible points where Z minus Z1 is a fixed amount. Okay, so that would actually make what's called a circle, okay, with the center being this point here, the fixed point. Okay, so it would be like a circle with the fixed point being Z1. So in this general case that I'm drawing, just to give you an idea, every single point on this circle, okay, the value of z minus z1 will always be that fixed amount A. Okay, that fixed amount A. The distance here between these two is the magnitude of z minus z1. This vector here, you can think of it as a vector. Its magnitude is z minus z1. And every point, if I now take this line here, okay, and I rotate it around, it's going to be z minus z1, that same distance all the way along here. Okay, that distance, the length of that line is z minus z1. The magnitude of that distance is z minus z1. So every single point along this circle, okay, satisfies that condition that z minus z1, its magnitude is equal to the radius of the circle, which we've called A here. Okay, so that's basically when you see a situation like this, it's talking about the locus of a circle, a fixed point from this particular position. But it has to be set up as in this way, where you have z minus, you have to have the modulus of z minus z1. Okay, and in this case, it's going to be less than or equal to 2. Okay, so that means it's not just a line, it's a region. In fact, it's going to be the whole region inside the circle. But in our situation here, our situation is not like this, it's slightly different. So I'm going to just get rid of this and draw our situation now. So I've just given you an idea of how this works. Okay, let's get rid of this stuff, including the circle. Okay, so now what we have to do is we have to express the modulus of z plus 2. Okay, so 2. Let's put it in a neat over here. The modulus of z minus 2 is less than or equal to 2. So this is, if I have to, z plus 2 is less than or equal to 2, we have to express this as a minus here. So what I'm going to do, I'm going to put z minus, and then I'm going to put here a minus 2. Okay, it's like you've got your complex number z is a plus bi. In this case, a is equal to 0, so our a is equal to 2, and our b is equal to 0. It's like you've got, a, which is minus 2 plus 0i. You can think of it like that if you want to. Okay, there's no I component. Okay, it's just minus 2. This will give us z plus 2. When I expand this, when I simplify this, it will give us exactly what we're looking here. But we need to express it in this way for us to make sense of what we're going to have. So this will tell us the coordinates of the center of the circle, basically. This will tell us this is the place where our z1 is. That tells us where our z1 is. Okay, so our z1 is going to have coordinates minus 2, 0, negative 2 on the real axis, and 0 on the imaginary axis. So it's going to be, say, over here. Just imagine this is negative 2. That's going to be our center of the circle, and our circle is going to have a radius of 2, right? So it's going to basically reach that axis there. Okay, so this is going to be our circle. Let me just make it a bit thinner. Okay, and let me just change its color to make it better to... Okay, so that is our circle. Okay, the center is negative 2, and the points, it's got an equal sign here, so we have to draw a circle which is solid. If it was said less than, then we draw it as a dotted line. If it was less than, then we would make this a dotted line. But now it's a solid line because it says equal to, so every point on there is included, and we got to consider all the values inside this circle, because it says it's all the points where z plus 2 is less than or equal to 2, so it's closer than 2 units from the edge of the circle, right? So that's this part drawn. So we've drawn that part there, and we have to just do the shading, but I'm not going to shade until we have to look at this, also this condition here. And what this means is the imaginary part of our complex number is greater than or equal to 1. Okay? So the imaginary part, we've got to find all the imaginary part is always going to be on the y-axis. Okay, so basically that means, we have to draw the line y is greater than or equal to 1. Okay, because we only consider about the imaginary part. The imaginary part is in the y-axis, so we're going to go to 1 here, and we're going to draw a line, and that line is going to be a solid line. Okay, and it's going to go through 1. So it's going to look something like this. Okay, it's going to go through 1, look something like that, and it's going to be solid again, as I mentioned, and we have to shade the region which is less than 2 units from the center of the circle, and also greater than this line y equals 1. Okay, so it must be above this line but inside the circle. So when we shade the region, we're going to shade this region over here, which is going to be like shading this part. This is the part that we need to shade. Okay, which is, this is basically the line y is equal to 1, right? So this is the region we need to shade. It's within the circle, less than or equal to 2, but above the line y equals 1. The imaginary part of z is greater than or equal to 1, means the line y equals 1, basically. If you said the real part of z, it would be a vertical line. We're talking about the real axis. So it means it must be, if it says imaginary part of z is equal to 1, it's going to be just this line. Here, it's going to be the region above it, but we want to shade the region which is satisfied by both of these. So we're shading this region here, which is above the line and within the circle. Okay, so there's the answer to part A. All right, so that's part A done for question number 5. Now we're going to go on to part B. So part B says, find the greatest value of the argument of z for points in the shaded region. So let's go back to the graph. So we want to find the greatest value of the argument of z. Now the argument of z, okay, is basically the angle made with the positive real axis. So if you think about the angle made with the positive real axis, and we could be, our value of z can be anywhere within this region here, anywhere inside this shaded region, at any point. But we can see that if we look at the biggest possible angle made, it's going to be the angle made, okay, with the last point there in that shaded region. So let me just do this. This will be the largest angle made. This angle with the positive x-axis, that will be the largest angle made. Okay, that will be the argument of z. Let's call the argument of z, let's call it theta. So we need to find the angle theta. Okay, that's the argument of z. Okay, where it's going to be the biggest possible value, right? The greatest value of argument of z. We're looking for this angle over here. Okay, this is the angle we're looking for. All right, so how to find this angle, that's our objective now. Okay, so now, if we think about it, okay, if I can find what this angle is, then this angle is 180 minus that. So let's call this angle alpha. And one of the things in the mark scheme, it mentions, labeling your points very carefully. Okay, so that's something that you have to take in, or labeling your angles, labeling your points, making it clear in your calculations what angles you're trying to find. So I'm going to call this alpha, I'm going to call this theta. Right, so how do we find this angle alpha? Right, now what I can do is the following. I'm going to make a line that joins these two together. Okay, I'm going to make a line that joins these two together here. this line, okay? And you know, one of the things I mentioned to my students with complex numbers, you should always bring with you a ruler when you're doing such questions, okay? When a ruler and a compass, right? Because a lot of times the loci questions involve circles, and if you draw a circle by hand, it's going to become really, it looks a lot messy, and then when you're trying to solve questions like this, it causes certain issues, certain problems, okay? So I think it's a good idea for us to use a ruler when you are answering such questions, okay? So now, what we need to do is find out what this angle is over here, all right? Now, what I would do to find this angle over here is there's a couple of things we could do. We could think of finding what this angle is in this section here, right? Now, I know this is 2. I know this is also 2, right? And I also know that this angle here, if I make a line from here to there, if I drop a perpendicular line from there to there, I know that this is a right angle. I've dropped a perpendicular line. I know that this distance from here to here is 2 units, from there to there. And this distance here is 1 unit. This is 1 unit. Okay, so if I can find what this angle is here, let me call this angle phi, then I can find what this angle is here by doing 180 minus phi. If I find this angle, then this angle can be found because this is an isosceles triangle. So there's a bit of thinking involved. So to find this angle here, I have a right angle triangle, I have the opposite, I have the hypotenuse. So I can say that the tan, and the hypotenuse, that's going to be sine. The sine of the angle phi is equal to opposite of a hypotenuse. So phi is equal to inverse sine of a half. Now, I'm going to, normally you deal with radians when you're dealing with Argand diagrams. So I'm going to put this as, that's going to be 30 degrees, which is pi over 6. So this is pi over 6 here. This angle here is pi over 6. All right, which means the angle over here is going to be pi minus pi over 6. So this angle over here, which I can call, for example, let's call it beta. Okay, so we can say the angle beta is equal to pi minus pi over 6. So the angle beta is equal to 5 pi over 6. Okay, so now we can find our angle alpha because this is an isosceles triangle. So we can say alpha is equal to pi minus 5 pi over 6 and then divided by 2. That's what this is going to be, because you've got to have the 3 angles here. This is also alpha as well. These 3 angles add up to 180. All right, so if I do pi minus this angle pi over 6, 5 pi over 6, pi minus beta, then it will be these 2 angles divided by 2 will give me one of them. So this is going to be pi minus 5 pi over 6 is going to be pi over 6 divided by 2 is equal to pi over 12. All right, so this angle here is pi over 12. So our angle theta is going to be pi minus, because the whole thing is 180 degrees, which is pi. Theta is pi minus pi over 12, which is 11 pi over 12. So we can say that the greatest value for the argument of z, okay, is equal to 11 pi over 12, and the steps are shown on the diagram. Steps on the diagram. Okay, so I would have written the steps here, looking at the diagram as I'm doing them, but because it's I have to keep going up and down and stuff, I just showed the steps here. Right, so I hope that's clear what we did. Okay, it might be a good idea for you maybe to label some of these points, but if you make it clear with the angle of what you're doing, So for this angle, I called it phi, right? This is 1 unit because it's, how far this line is up from the along the y-axis. And this is 2 units because it's the radius of this circle. Okay, so that's 1 and 2. We can find this angle, which is inverse sine of 1 over 2, which is pi over 6. Therefore, we can find beta, which is 180 minus that, or pi minus that, which is 5 pi over 6. Once we found beta, we can find alpha. Why? Because alpha is part of this isosceles triangle. This is 2, this is 2. So we can say 180 minus this angle. Okay, we're finding now, that was finding alpha here. That's the alpha part there. Okay, 180 minus 5 pi over 6, okay, over 2. Okay. This is like, this here is phi basically. Okay. No, this is beta, sorry. This is beta. Okay. So basically we found 180 minus beta divided by 2. That gave us alpha, which is pi over 12. We need the angle from the positive x-axis until it reaches this line, okay, which takes us to the, so basically the largest angle, okay, that is made by joining, the origin to a point within this shaded region. Okay, so it's right up to the end here. That would be the largest angle you can form. If I try to, connect it to any other point in this region, the angle is going to be smaller than that. The largest, anywhere in this region, that's going to be the biggest possible angle, and you connect it to that last point where the shading is. Okay, so that is how you then find theta. So that's the argument of Z, 11 pi over 12. Okay, so I hope that was clear. So other questions from this particular paper can be found in the playlist that will appear in the top right of the screen at the end of this video. Other questions from the topic of complex numbers can be found in the playlist over here. In particular, Argand diagrams, I'll put a special playlist for those in this playlist over here. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.